Before we go over the solution to problem 14 on the 2024 AIME, I'm just gonna go over some basic linear algebra concepts. So I'm gonna go over dot product, cross product, and using the dot and cross product to basically find the equation of a plane given any 3 points A, B, C. If you want to skip ahead, I put the link in the video description. Just skip ahead to whatever timestamp I put down there. And also, I have some very in-depth linear algebra notes, which you can find in the description. So yeah, if you want any further guidance in what I'm gonna go over. Okay, so let's first go over the dot product, right? So what is the dot product? Well, the dot product of two vectors, v1 and v2. Vectors are just arrows, right? So vectors v1 and v2. We write the dot product like this, v1 dotted with v2. And this is basically defined as the magnitude of v1 multiplied with the magnitude of v2 times the cosine of the angle formed between those two vectors. So let's say I have two vectors that are coming from the same point, right? And I have vector v1 like this, v2 like this. This is their theta right here. So the dot product is basically going to be the length from this point to this arrowhead of v1. That's the magnitude of v1. The magnitude of v2 is the length from this point to the arrowhead of v2. So we have magnitude of v1, magnitude of v2. And then cosine of theta is just the angle, the cosine of this angle formed between them. We don't generally use this too much unless the vectors are perpendicular to each other, because you can't find the cosine of any angle unless you use a calculator. What's cosine of 32.5? We don't know, right? But if vectors are perpendicular to each other, if v1 is perpendicular to v2, then this cosine becomes 0. So if the dot product of two vectors is equal to 0, then we say those vectors are perpendicular, because then cosine becomes 0. And another way, so we express vectors, we express 2D vectors like this, x, y. Where this is their x component, this is their y component. What does this mean? Well, this means when a vector starts from the origin, this is basically the coordinates of its arrowhead. So the arrowhead of any vector, so let's call this vector vector w. So this is vector w, right? So that means the arrowhead is basically going to be right here, x comma y. So that's what x, y means. And we can do something pretty similar for 3D vectors. We'll have, we'll just add an extra z component, right? Because we are going into 3 dimensions. So we have x, y, z, and then in 3D space, that's going to be from the origin and then the vector's arrowhead in 3D space. This would be x, y, z of vector w, if this is vector w. Okay, so now that we know how to basically notate vectors, right, there's actually a pretty cool way to do the dot product with two vectors. So let's say I have two vectors, x1, y1, and I want to dot it with another vector, x2, y2. Well, I don't really want to get messy with cosines and everything, so what we can do instead is we can just multiply their x components like this, x1, x2, and we can multiply their y components, y1, y2, and we obtain a new vector. And this new vector is their dot product. So this new vector is a dot product which has both magnitude and direction. So yeah, that's pretty useful. So this is basically the basics of dot product. I don't think I need to really go over more here, because that's basically all you need to know for this problem, right? So now what we're going to do is we're going to delve into cross products. So cross products, keep in mind, cross products are only for 3-dimensional vectors. They do not work for 2D vectors, and I'll show you why right now. So cross product is basically defined as given two 3D vectors. Let's call these vectors again v1 and v2. So let's say v1 is like this, and then v2 is like this. Given two 3D vectors, v1 and v2, their cross product is defined to be the vector perpendicular to the plane formed by these two vectors. So their cross product is basically this vector that's perpendicular to these two vectors, right? And to figure out which direction it's extending in, there's actually this thing called the right-hand rule, but that's a bit too complicated. I don't need to go over that. Just know that cross product is the vector perpendicular. The cross product of two 3D vectors is the vector perpendicular to the plane formed by them. So the cross product, we write it as v1 x v2. Let's say the cross product is v3. So this vector would be v3. Now, similar to the dot product, which was multiplying all of the x and y components, there is a way to calculate cross product. And I actually don't have it memorized, but there's a pretty cool shortcut. So in vectors, so we have any arbitrary vector x, y, z, right? This is the x component, y component, z component. Well, in linear algebra, what we actually like to say is any arbitrary vector can be written as I hat, j hat, and k hat. These are just this is just fancy notation for the x-coordinate component, y-coordinate component, and z-coordinate component, right? So that's just some context to a little shortcut I use for calculating the cross product, right? So let's say I want to find the cross product between two vectors, ABC and DEF. So what you can do is you can write a determinant like this. If you don't know what determinants are, that's okay. Just kind of memorize the steps I'm going over here, and then let's see. So yeah, so you can write a determinant like this. Write the vectors horizontally, ABC, DEF, right? And so yeah, I just wrote these at the top so that we know where to place the x, y, and z components. Remember, these are the x components, which go underneath I hat, y components go underneath j hat, z components go underneath k hat. And what we do is we copy over this portion, and we copy it again to this side. So now we have something that looks like this, right? So what we do is we go by diagonals. So and then we're gonna take the product. So these variables are all gonna be numbers, right? Except for the I hats and j hats I wrote on top. All the variables are gonna be numbers. So these diagonals are gonna evaluate to numbers. So we don't care. Again, we're not the k hats, I hats, j hats. Those are just like placeholders. So we're not gonna multiply them with our product. So our product, we're just multiplying d and b, e and c, f and a. I hat, j hat, and k hat just tell us what those are. So like d and b give us the z component of the cross product, right? So they're just little placeholders that tell us what they are, what they mean, right? And then we'll take diagonals going down. So we'll take diagonals looking like this. Okay, so now we have a lot of messy diagonals, right? So what I like to think of it as is basically read this determinant basically from left to right. And then what you want to do is you want to add all the downhill pointing diagonals. So like this is a downhill pointing, this is a downhill, this is a downhill, right? And then what you want to do is you want to subtract the uphill ones. And you can think of it as like walking up and down a mountain, right? Going up a mountain feels really bad, so you can call that negative, right? So you're subtracting it. And going down a mountain feels like much better than going up, so you can call that a positive. So we want to add the diagonals pointing down when we read from left to right, and we want to subtract the diagonals pointing up. So this allows us to just figure out what the cross product is. So the cross product is basically the x component of the new cross product vector is going to be bf minus, and then we look for the I hat, right? E and C. So BF minus EC. The Y component, or J hat, is going to be, let's see, FA, because that's pointing up, minus CD. And the K hat component is just going to be AE minus DB. Okay, so yeah, and so now that we have the I hat, J hat, and K hat components, or X, Y, and Z components, we can say the cross product of two vectors a, b, c, d, e, f gives us this new vector with x coordinate bf minus ec, y coordinate fa minus cd, and k or z component ae minus eb. So pretty cool, right? You don't have to just memorize this formula. You can just like kind of derive it on your own. So yeah, so that's how we find cross product. And the cross product again is just basically, right? We have a plane formed by two vectors. The cross product is the new vector, which is perpendicular to this plane. Okay. So now what I want to do is just briefly go over, like, let's say I have a point A and another point B, and I want to figure out a vector which goes from point A to point B. So this is actually relatively simple. So let's say we have a coordinate for point A, x1, y1, and we have a coordinate for point B, which is x2, y2. What we want to do is we just want the change, right? We want the change in y and we want the change in x. And that's basically going to be our new vector. So the vector going from point A to point B is going to be the change in y, or let's do change of x first, right? So x2 minus x1 for the x coordinate of the vector arrowhead, and then y2 minus y1 for the y coordinate of the y arrowhead. So think of it like walking from point A to point B, right? And then you want basically your change. So that's going to be your change. So the vector going from point A to point B is this vector with x component x2 minus x1 and y component y2 minus y1. Okay, so now that we have all of that figured out, let's use cross product and dot product to find the equation of a plane given any three-dimensional points, A, B, and C. Okay, so let's say point A has coordinates A, comma B, comma C. Point B has coordinates D, comma E, comma F. And then point C has coordinates G, comma H, comma I. And so we have this plane, right? We want to find the equation of this plane. And so the general form, like standard form for lines, and like standard form for most other shapes, like the standard form of a line is like ax plus by plus c equals 0, right? So for a plane, it's going to be ax plus by plus cz plus d equals 0. Because we have this extra z component, right? So, and then the constant just gets moved over. So this is the standard form for any plane, right? So we basically want to find this equation. Okay, so let's first take any two arbitrary points on this plane. Let's say those two arbitrary points are x1, comma y1, and x0, comma y0. Okay, so arbitrary points, right? So these are two arbitrary points on the plane. So we can plug them into our equation. ax1 plus by1, or wait, I forgot the 3D z component, my bad. Let me, y1, comma z1, comma z. So we have, okay, so we have this equation, right? And then we have another equation, which is ax0 plus by0 plus cz0 plus d equals 0. You can maybe see where I'm going with this now. So what I'm going to do is I'm going to subtract these two equations from each other. So then what are we going to get? Well, we're going to get a times x1 minus x0 plus b times y1 minus y0 plus c times z1 minus z0. The d's cancel out. So this is our new equation when we subtract those two, right? Again, x1, y1, z1, and x0, y0, z0 were just any two arbitrary points on the plane. So like they could be here and here. Those could be our 2 points. So remember what I said about dot product. Like this also applies to 3D vectors. The dot product of ABC and DEF, we just multiply all their components. So AD, BE, and CF. This equation kind of looks like a dot product, right? So what is it? What is the dot product? Like, how can we write this as a dot product of 2 vectors? Well, let's first bring out all the a, b's, and c's. So we can say this is a dot product of vector ABC and vector x1 minus x0, y1 minus y0, and z1 minus z0. And this is equal to 0. Aha! So the dot product of these two vectors is equal to 0. So that means these two vectors are perpendicular to each other, right? Now, what does this vector exactly mean? Well, remember, to find a vector going from 2 points, you just subtract their coordinates. So this is just any vector lying on the plane, because it's a vector going from this point to this point. So it's a vector lying on the plane. So this is basically saying ABC is perpendicular to any vector lying on the plane, because the dot product is equal to 0. So we actually call vectors perpendicular to planes normal vectors, right? So we can say in any plane ax plus by plus cz plus d equals 0, the vector perpendicular to this plane is a, b, c. Okay, so this is really cool now, right? But how is this exactly going to help us find the equation of our plane, right? So let me bring back, so now that we have this established, right? So I said that we had 3 arbitrary points on our plane, A, B, C, and then this had coordinates A, comma, B, comma, C, D, comma, E, comma, F, G, comma, H, comma, I. So we can do something very smart here. What we can do is, to define a plane, we need a vector going from A to B, and we need a vector going from A to C. And then we want to take their cross product. And their cross product is going to be ABC, right? Because that's the vector perpendicular to the plane. So what's the vector going from point A to point B? Well, again, we can just subtract their components. So the vector going from point A to point B is going to be D minus A, E minus B, F minus C. And similarly, the vector from C to A is going to be G minus A, H minus B, and I minus C. So now we have 2 of these vectors, and they form a plane, right? So we can say the cross product of D minus A, E minus B, F minus C, this crossed with G minus A, H minus B, I minus C, is going to be equal to some vector V. So let's say we evaluated this cross product using the shortcut I found, and then we found that the 3 numbers were J, K, and L. Then we could say this is equal to A, B, C, because in our, and A, B, C, again, that has no relation to any of the points or what I'm saying in this problem. A, B, C are just the coefficients, right? So the coefficients of our equation of the plane. So our equation becomes Jx plus Ky plus Lz plus some constant d equals 0. So all that's left is to find this constant d. And to do that, all you have to do is plug in one of these points. So if I plugged in point A, B, C, then I would get like Ja plus Kb plus Lc. So this evaluates to some number, and then plus d equals 0. So d equals the negative of whatever this number evaluated to. And then you have your equation of the plane, right? Because you found d, and you already have all these coefficients. So that's how you use linear algebra to basically find the equation of any plane given 3 points, right? So yeah, that's basically what I wanted to go over before we, got into solving the 2024 AIME 1, because that involves, my solution basically involves finding the equation of the plane, forming one of the tetrahedron bases, and then one of the vertices of the tetrahedron, so like vertice D, and this was like ABC or something, I don't know. So the distance from this point to this plane would be the height of the tetrahedron, and we can find that using the distance formula, ax plus by plus cz plus d over square root of a squared plus b squared plus c squared, right? This is the distance formula from any point to a plane. We could use that to find the height of the tetrahedron, and then we have point I lying somewhere like in between this and D, right? So I actually forms 4 congruent tetrahedrons. It forms because all the faces are congruent in the problem. So I ABC and then I A D whatever. So it forms 4 congruent tetrahedrons with each of the faces, and then we can basically find an equation, and then we can find what I is, because the area of the bases stay the same, right? So you'll see more of that in the solution. But yeah, I basically just wanted to go over some basic linear algebra concepts here. I hope you found this portion of the video helpful. But yeah. Let's solve problem 14 on the 2024 AIME 1. Okay, so the problem gives us this tetrahedron ABCD, and it basically says like AB equals CD equals root 41, AC equals BD, which equals root 80, and BC equals 80, which equals root 89. Okay, so let's try to see if we can relate each of these sides to Pythagorean triples. So what do I mean by that? Well, like 41, for example. We can write 41 as 5 squared plus 4 squared, and then we'll have this right triangle, right? 4, 5, root 41. Now, why is this useful, right? Well, the reason this is useful is because then we can inscribe it in a right rectangular prism. And then that makes things a lot more easier with like coordinates and stuff, which we're probably going to have to use. So let's do that for all the other sides. So 80 can be written as 8 squared plus 4 squared, and 89 is just 9 plus that, so 8 squared plus 5 squared. Okay, so now we can inscribe this tetrahedron in a right rectangular prism, and then we can label that prism's dimensions, right? So, okay, so this is a rectangular prism, and it basically has a width of 4, height of 5, and a depth of 8. Okay, so now let's let C be the origin. So let's let C be 0, comma 0, comma 0. Okay, so if that's C, then point D, where's point? That's point D, right? So point D is going to be 4, comma 5, comma 0. A is going to be 4, comma 0, comma 8. And B is going to be 0, comma 5, comma 8. Okay, so now what we essentially want to do here is we want to find one of the planes, like the equation of one of the planes. And then if we can do that, then we can find the distance from one of the vertices to that plane, and that gives us the height of the tetrahedron. And then what we can do is we can say, okay, so the tetrahedron is formed by point I, B, and C, I, A, and B, all of those. They're all going to be equal volumes. So we have the base area, we have the height area. We can divide that by 4, and basically the height of each of these 4 small tetrahedrons is going to be the answer. So yeah, that's what we want to do. So the first step to finding the height of this overall tetrahedron is finding the equation of one of the planes. So let's say we're trying to find the equation of plane ABC. Okay, so let's find the equation of plane ABC. So first off, we want to write down the points of this plane. So the points are going to be 4, comma 0, comma 8, 0, comma 5, comma 8, and 0, comma 0, comma 0. Okay, so to find the equation, basically what we want to do is we want to find one vector. So like this was point A, right? So that was point A, and then we had point B, and we have point C, right? So we want to find one of the vectors here, and then basically what we want to do is we want to take the cross product of one vector, so like let's say the vector going from point A to point B. We're going to cross that with the other vector in this plane. So, and yeah, and so once we cross those two, so we can take a vector going from A to B. So like, let's say these are our 3 points, right? So we can say the cross product of this vector and this vector, and that's basically going to give us it's going to give us a new equation, right? And that vector, which is the cross product, is basically going to be perpendicular to the plane. So then we can say the dot product of that and one of these points is going to be equal to 0, right? So let's find the cross product of 2 of these vectors. So let's first find the vector going from A to B. So the vector going from A to B, so 4 minus 0 is 4, 0 minus 5 is negative 5, and 8 minus 8 is 0. Wait, there are no commas. So 4, let me actually just clean things up a bit. So let's just call the vector going from A to B V1. So v1 is basically going to be 4, negative 5, 0. We basically just subtracted the coordinates, the coordinates of A from the coordinates of B from coordinates of A. And then we can do the same thing for vector 2. We can basically take the distance from the vector going from B to C. Since C is the origin, that's just going to be B. So vector 2 is just going to be 0, 5, 8. Because, again, 0 minus 0, 5 minus 0, 8 minus 0, those are just going to be the same numbers. Okay, so now what we want to do is we want to find the cross product of these two vectors. Basically, the cross product is this parallelogram formed by these two vectors, and it also defines this height, which is perpendicular to this parallelogram. So that's what we want to find. So how do we find the cross product? Well, there's actually this really neat shortcut. So what we can do is basically we can have a determinant like this, and then we can have I hat, J hat, K hat, and then we can just write the vectors out like this. So then we have like horizontally, so 4, negative 5, 0, 0, 5, 8. And then we can write out another determinant, which is I hat, J hat. We basically just copy over this portion. 4, negative 5, 0, comma 5. Now what we want to do is we'll just go by diagonals like this. These are the 3. And then we'll do the same for the opposite direction. This is really messy, I'm sorry. And then basically, what I like to think of it as is like reading it from left to right. And then basically, you want to think of the ones going down as being positive because like going down a hill feels good, and like going up a hill feels bad. So subtract off the up hills. So I hat, J hat, and K hat are like the components. So like I hat's gonna be the X, J hat's gonna be the Y, and K hat's gonna be the Z. So now what we have to do is we have to basically take the product of each of these diagonals going down, and then we'll subtract them from the diagonals going up. Okay, so let's do that now. Okay, our first product is gonna be for I hat. So I hat. Right, I hat is going to be negative 40 minus negative 5 times 0, which is going to be negative 40. J hat is going to be 0 times 0 minus 32. And that's just going to give negative 32. And then K hat is just going to be 5 times 4 minus 5 times 0, which is 20. So the cross product of v1 and v2 is negative 40, negative 32, comma 20. So this is the cross product of the two vectors. Okay, so now what we want to do is we want to take this cross product, right? Basically, this cross product is going to be perpendicular to a plane. So that means that the cross product, which is this, dotted with any point in our plane is going to be equal to 0. So the dot product of this and any point in the plane, so like let's say we chose like 408, right? So 408, this is going to be equal to 0. So what does that mean, right? So let's take the dot product of this first of all. So we're going to multiply, so negative 160 minus 32 times 0 plus 160 plus some constant d equals 0. And so basically, so negative 160 plus 160, that cancels out, and then negative 32 times 0 is 0. So this actually itself evaluates to 0. So that means d is equal to 0. So like in the equation ax plus by plus c plus d, d is going to be equal to 0. So we found d, right? Okay, so now that we found d, what we can do is we can basically take this cross product, and then we can say the equation of the plane is going to be negative 40x minus 32y plus 20z plus d, which is 0, is going to be equal to 0. So this is the equation of the plane. And then we can just divide by 4 to get 10x plus 8y minus 5z equals 0. So this is the equation of plane ABC. And now what we want to do is we want to find the distance from one of the vertices of the tetrahedron to this plane. So let's say we chose point D, right? So what's point D going to be? Well, point D is going to be 4, 5, 0, right? And so the distance from that is going to be the absolute value of ax0 plus by0 plus z0 all over square root of a squared plus b squared plus c squared. Okay, and so now we just have to find that. So let me do that real quick. So that's going to evaluate basically to 10 times 4 plus 8 times 5 plus 0, this absolute value, over the square root of 10 squared, which is 100, 8 squared, which is 64, and 5 squared, which is 25. And this simplifies to 80 over root 189. So this is the height of our tetrahedron, right? So now, basically, the key thing is that we have to basically find the volume of this tetrahedron. So we have this height, right? So the area of the tetrahedron is 1/3 base times height, which is 80 over root 189. And, okay, so let's call I the distance from, I is basically the answer, right? The distance from the center to each of the planes. So let's call I that, right? So what we basically have is 1/3 times the area of each of the smaller four. So let me bring up the visual again. So let me see if I can, yeah. Okay, so basically the distance from I to each of these faces, right? That's still, the area of each of the faces is going to be b, right? So the area of the faces is still going to change. But the height is going to be I. So now we have this equation, right? So, and then there are 4 of them. So there are 4 of these. So we basically have, now all these things cancel out, right? So we're left with I is equal to basically 80 over root 189 over 4, which is 20 over root 189. And that's basically going to simplify to 20 root 21 over 63. And then so we just add them up. So 20 plus 21 plus 63, that gives us our final sum of 104. So 104 is the final answer for this problem.